VGG, the name of this comes from Visual Geometry Group, and this is at the University of Oxford. So the VGG network is really fairly straightforward. It is a sequence of convolutional layers followed then by some linear layers at the end. All of the convolutions are 3 by 3, convolution layers, max pool layers, and then at the end, flattening into some linear layers. The activation function that's used is ReLU. So it looks something like we'll have a conv layer, followed by another conv layer, followed by a max pool. I'm going to assume after each of the conv layers we have a ReLU. And then we could do, let's say, another conv layer by conv layer by max pool. And we do this, well, let's say 4 or 5 times. The VGG actually is a family of models. So there's VGG 11, VGG 16, VGG 19, depending on how many of these convolution layers that we have. So we feed in an image. Let's say it's a 224 by 224. We have this 3 by 3 conv, and we start out with, let's say, 64 of these. So after the convolution layers, so our input is 224 by 224 by 3. After here, we'll still have 224 by 224, but the depth is now 64. Okay, and these convolution layers are actually 3 by 3. This one's 3 by 3 by 3. This one is going to 3 by 3 by 64. Coming out of here, let's just use a different color for this. So this is now going to be 224 by 224 by 64. We go through a max pool, which makes it smaller. So this will now be 112 by 112 by 64. Right, so this is a 2 by 2 max pool. Now that we have decreased the horizontal and vertical dimensions, we go ahead and increase the depth. So instead of having 64 convolution layers, we'll bump it up to 128. So out of this 128, and these, of course, are going to be, now this is going to be 3 by 3 by 64, because that is the input size. This convolution is going to be 3 by 3 by 128. Right, why is that? Again, we remember that if we have a convolution layer here, 3 by 3 by something, that it has to match whatever the input is. So the input may be larger, so the horizontal and vertical direction could be bigger because we can take this convolution and move all the way through, but the depth matches. So our output here now 112 by 112 by 128. Similarly, we're going through, so we'll do a few convolutions, we'll do a max pool, the max pool will reduce the dimensions, and we'll then go through and increase the number of convolutions. So we'll have 256 here and 256 here, and then eventually we'll have 512 and 512. So it'll shrink down from 112 by 112, down to 56 by 56, to 28 by 28, to 14 by 14, finally to 7 by 7. And in fact, that's what the final output layer is. So the final convolution layer, the output is 7 by 7 by 512. This now gets flattened into a single long vector of size 7 times 7 times 512. So that looks like it's what, around 50 times 512, so that's around 25,000. This gets fed into a 4096 fully connected layer. That gets fed into another 4096 fully connected layer. We'll have ReLUs after each of these, of course. And then finally, that goes into a 1000 fully connected layer. Finally, through a softmax. That's the architecture of the VGG. One thing to note is the vast majority of weights are out here in these fully connected layers. Okay. Like more than 90% of the weights are found in here. This contrasts quite a bit with the inception architecture. So one question might be, I mean, we've done this careful crafting, where so we have 3x3 convolution, 3x3 convolution, and then a max pool, some more convolutions, and then a max pool, some more convolutions, and then a max pool. How do we know a max pool would be good here? How do we know it wouldn't be better to just have another convolution? How do we know this is 3x3 and it wouldn't be better being 5x5, right? Or 1x1? We don't really know, and that's going to lead us in to our next architecture choice.